on this computer. Share screen. Share. All right. So hopefully you've had the chance to look at the videos for this week, which were pretty sparse, actually, right? We had 3 videos this week. So we had one on the Monty Hall problem, which we're going to go over today. So I hope you had the chance to watch that. I will take a look at your question. If you have quiz issues, I can handle those after class for quiz 3. Okay. So we had this video about the Monty Hall problem, this video about the Monte Carlo simulations in general, and then I had this video that seemed pretty random about like carnival scam science, which basically, if you watched it, was just basically somebody looking at all the different games that are carnival games and figuring out why they are issues. Yes, I can do demos today. Why people have issues with it, but why is it relevant to this one? Well, because the way he found out how hard the games were, if you watch the video, was that he had his friends go and basically sit at the down at one of the tables and just watch the games and keep track of the outcomes, basically marking whenever somebody won and lost. Now, this is what we call a Monte Carlo simulation. That is what it is in the raw in the most kind of natural form. Monte Carlo simulations are all about they kind of have their origin in the idea of gambling, as most of statistics does, and this is not necessarily me endorsing gambling. It's just that there's a lot of games that are gambling games that are well understood, right? They are well understood games. So Monte Carlo simulations are named after the famous gambling city that's located in Monaco. Now, Monaco is one of those micronations, one of those nations that basically are like, oh yeah, that's totally a country, even though it's really, really, really small. So, so for instance, if we were to look at, click on Monaco on Google Maps, right? That is the entirety of the country of Monaco. Let's zoom out a bit further. Yeah, pretty tiny. Another micro country not too far away is, I mean, it's smaller than our classical very small country of Luxembourg as well as Liechtenstein. Although very few people point out that Andorra is actually a very tiny country, just situated in between France and Spain. It has very interesting form of governments. Don't worry about the alternating series. It's the point about math is that math is hard, and we don't like hard math. At least we don't like hard math in this class. Hard math is terrible. So we're going to just do it. The entire objective of this Monte Carlo stuff is to have fun while making math super easy, because math is hard, but counting is easy, and computers can count really fast. That's the entire idea of Monte Carlo simulations. So, but where does that come from? Well, again, that comes from the idea of the city of Monte Carlo, which is a famous gambling city with a lot of gambling in it. That is that's located in Monaco. So it comes from this, and basically the idea of a Monte Carlo simulation is pretty straightforward. I don't know what my chances of I've got some outcome I want to observe, like a game or drawing balls from a bag or rolling dice. Like let's say I grab let's say, like, say say you've got, I've got a bunch of dice that I just want to roll, right? Say I've got a bunch of dice over here in my hand that I want to roll, all sorts of different sides and stuff. And I want to say, what is the chances that I roll? Well, what are the chances that I roll a 32 on these dice, right? Now you could figure that out with math and statistics, but that's boring and hard, right? You'd have to do about, you'd have to look at like expected outcomes and stuff. So what a Monte Carlo simulation says is what I'm going to do is that I'm going to create random number generators on the computer, and I'm going to have the computer roll the dice like 500,000 times. And that should probably be close enough for me to figure out what the outcomes are. Okay. So that gets me into, before I completely forget about it, this is a perfect time to bring up the final exam that you will have during the final exam period, which is farther away. Last semester, I had 3 questions. I see no reason to change that. And I did tell the class the contents of the questions. So one of the questions will be a Monte Carlo simulation, which is last semester, I had the students analyze a board game. I said, here's the board games, here's the rules. It's a cooperative board game made for 2-year-olds to learn how to take turns. And my question was, how often do the players win? Because it's, complete roll of the dice, right? So that was for them to, and the answer was about that, basically that you won about 60% of the time. So not 3/4, but that was the kind of question that I was asking on the exam. So that's something, so I'm telling you now, you are guaranteed to get a question that is a Monte Carlo simulation on your final exam. And it will probably be something like, here are the rules for a game. Please tell me here's the rules for the out of the game. Please tell me what the chances are of these outcomes occurring for the game, or depending on what the game is, the outcome of a specific roll, right? So, and before the final exam, we'll go over, plenty of practice problems. We might look at like some simulations for Catan and stuff. I might introduce you to some board games as a result. So anyway, and this is very close to the idea of what we got with statistics, where a lot of early statistics came from analysis of gambling games. And yeah, they solved that mathematically, but again, we're going to solve that by doing counting. So we've messed with pi. So this one's pretty cool, and I'm going to show you guys this one. So you've probably remember we've messed with pi before in this class, and we know it's an irrational number, basically that it goes on forever, it never repeats, right? You don't get a fraction that is equal to pi. Well, aside from pi over 1, that equals pi, but obviously that's not what they mean. And there's a lot of different ways to approximate pi, right? We were looking at that earlier when we looked at this Wikipedia page much earlier in class about different ways we can add converging series to get pi. Like this one was one we did. Pi over 4 is equal to 1 over 1. And if that's a good one to review. That was quote unquote fun, but Monte Carlo simulations are way more fun and more intuitive to understand. So this is what we call, so we're going to use what's called the Dartboard method for approximating pi, which is the idea is that we're going to create a square and a circle and a square. Okay. So suppose you're throwing darts at a dartboard. Most of the darts are going to hit the board and some are going to miss. So we're interested in exploring the number of darts that hit the dartboard and the number of overall darts you throw. So the idea here is that let's go ahead and create a whiteboard to go along with this so that we can kind of see what we want to happen. 1 second. There we are. 1. Why am I always this disorganized? Because I am. It's just the way I am, and it works. It adds, I feel like it adds a frenetic pace to the class. All right, so the idea here is that we want to draw. Okay, boom, boom. Okay, the idea here is that our dartboard is a unit circle that is centered at 0, 0 with a radius of 1.0. So we're defining the problem right now. Ink to shape. So let's go ahead, create a circle. Can we, is it able to recognize that I want a circle? Insert. Well, let's try one more time. Hey, it recognized that. So it recognizes me doing a square. Does it recognize me doing a circle? Hey, okay. So it does work. That's pretty cool. That is pretty cool. One more time. Oh, whatever. Okay, so we've got our badly drawn unit circle. It is centered at this point, 0, 0, right? And we're going to say it has a radius of 1. Okay, so this point over here would be 0, 1, and this point over here would be 1, 0, and we've got also, for your consideration, -1, 0, right, as well, right? It is a circle with a radius of 1. So our dartboard is in the middle of a square that is 2 by 2. Let's go ahead and, so our dartboard is inside this square, okay? Make sense? This dartboard is inside the square, and there's some kind of magical force field that basically says the only place a dartboard can land is inside. All darts are going to land inside the square, but whether or not they land inside a circle, right? I'll throw a dart, it'll land here or here or here or here. Sorry, it won't land here, but it will possibly land here, right? It's always going to land inside the square. Make sense so far? Every guy got that so far?
Yeah. Okay.
So now we can, so how would we possibly simulate the throwing of these darts? Well, we generate 2 random numbers. One random X coordinate between -1 and 1, and 1 random Y coordinate between 1 and 1. That will give us a precise place where a dart will land. We know the dart lands, and then we can use some math to figure out where the dart lands. We know if the dart lands in the circle, if it's less than 1 away from, if it's 1 or less away from the radius. Basically, so use the Euclidean distance formula to figure out, hey, if this is greater than 1, then it's outside the circle, right? Take the X coordinate, square it, take the Y coordinate, square it, get the square root of that. That's our classic Euclidean distance formula, although I have to look it up every time because that's me. And you know, math is hard. So, but not really, it's just that math looks hard, and they do these crazy symbols that make everything look hard instead of writing things out, which is dumb. Okay, since the area is pi r squared, okay, so the area of the circle, an area of any circle is pi r squared. We know our radius is 1, so the area of this unit circle is what? All right, so it's pi r squared, which is equal to pi 1 squared, because it's got a radius of 1. So we're just going to be basically dealing, so this thing's area is pi. And we know this is a 2 by 2 board. So this is a 2 by 2 dartboard also. We know that much. So the total area of this thing is 4, of the square is 4. So the ratio of the darts that hit the dartboard, right, will be the ratio of stuff that hits inside the dartboard to the ratio of stuff that to the total number of darts thrown will be pi over 4. right? So this is all the stuff that lands inside the dartboard, pi. All the darts thrown are going to land inside the square, which is radius 4. So this is actually, so if we take this, we can get pi over 4 from this. It's kind of a weird little trick. So how are we going to do this? Well, I'm going to have some fun. We're going to do it with turtles. What? Turtles? Really? For this? Well, yeah, if we're messing stuff around, we should totally do it with turtles. So let's go ahead and import turtle. Right? Let's actually like physically throw our turtle around onto this dartboard and, you know, see where stuff lands. So we're going to import a turtle. Okay. So let's see. So we want to do the animation before we do too much math. You should review. So, yep. Okay. So we're going to need a couple of things. The first thing we're going to need is, it says you should review the win.setWorldCoordinates function. That did not search with Google instead. There we go. I don't want a URL. I want, there we go. We want docs. Give me the docs. Set world coordinates. So I forget how to use this because I use this like once a semester, like now. So what it does is that basically it says it sets up the user defined coordinate system rather than using the normal coordinate system. So it gives me the upper left X and upper right, sorry, upper left X and Y, and sorry, the lower left X and Y and the upper right X and Y. So basically it's saying, what are the corners of what are the coordinates of the corner in the board? So, okay, that's no problem. All right, so boom. Boom. Okay, so import turtle. So we're gonna make Bob, he's gonna be our dart today. I'm sure he's very thrilled about that. Turtle left turtle. Okay. And then we need the window. We need the window. How do we get the window? Oh, we can just simply say screen.reset. Okay, so how do I get the screen? So let's see. Win is equal to turtle dot. Let's look at all the functions up here. How do I get the window? We have. So we have, it's probably somewhere wherever we see turtle. So, the screen gives us a turtle screen. There we go. And let's go ahead and just copy paste. So let's first off make sure that I didn't break anything. Good, it's not yelling at me, so that's a promising sign. Set world's coordinates. So the lower left of this is going to be, so lower left over here, coordinate. The lower left of this is going to be -1, -1, -1. That's the lower left corner of the square. -1, -1, and 1 and 1. Does everybody follow that? Why that is?
Can I ask a question?
Yes.
Why isn't win equals bob.screen?
I need turtle.screen because it's inside this function.
Okay.
So sorry, it's inside the turtle package. So I'm saying window is going to be make me a new window using the screen function. That's what I'm saying. Just like I'm saying, make me a new turtle called Bob using the turtle function.
Okay.
Right. So here I'm getting access to the window. Let's test this out. I'm going to say bob.go to 1, 1. And if this looks, this looks familiar to you at all, this is because it's kind of what your hurricane tracker program did to set the longitude and latitude to correctly, so that when you move to the proper longitude and latitude, the turtle moves accordingly. It's at the coordinates, like the coordinate system like that. So here, as you can see, 1, 1 is this top corner. And if I told him to go to -1 and 1, -1, -1, he'll go to that corner. So great, we set up our square, as everybody can see. Now we just need to start throwing darts, I guess. Let's see what it says. So every time we throw a dart, we should make a dot on the screen where it lands. If you color the darts that hit the dartboard blue and the darts that miss red, you'll definitely see a circle emerge as the simulation progresses. Okay, so let's go ahead and import random. Okay, so how are we going to throw a dart? Well, what I'll do is I'll say, well, first let's go ahead and throw 10 darts. So four in range. Let's do a for loop that just does something 10 times. Okay. So how do I throw a dart? Well, first things first, Bob, you got to take up that pen because we don't need to see you dragging everything all over the board. That's not the way darts work, right? We take a dart and we throw it, and then we pick it up and then we throw it again, right? So Bob.pen up. Okay. And so right error. Oh, right. Pass. Run. Okay. Yep. And then this doesn't do anything because I didn't tell Bob to do anything. Great. Okay. So what we're going to do now is that I'm going to tell Bob to go to, what we're going to do is we're going to throw the start by generating a random X and Y. So X is equal to random dot rand int, I believe, from -1 to 1. That will give me a number between -1 and 1 inclusively. And we'll just simply say this for Y as well. And so Bob.go to X and Y. Right, that just gives, and so he's just gonna flit around the board now, I hope.
Didn't you get rid of like the set world coordinate?
Did I get set? Oh, why did I get rid of the set world coordinates? That's silly of me. Let's go back into my history and get that. I don't know why I did that. So Bob.set world coordinates. We got that again. Copy, paste. Why did I do that? That seems silly. So there we see Bob kind of just jumped all around the screen. How'd that happen? All right. So, right. Didn't I say Bob.pen up? I think go to.
I can't quite see. Do you think you can zoom in a little?
Yeah. Sorry. Bob.up. He really is. Why are you dragging that pen around? Bob.go to XY. So Bob.up. Pen up, no drawing when moving, right? It's pen up, PU or up. It should work. Bob.pen up, run. Okay, there we go. I think. Let's make sure. Maybe it just didn't like being inside of there. Okay, so we've got him moving. So now we need to see where he's been because he's moving quickly. So what we're going to do is rather than having him draw, we are going to tell him to move somewhere, and then we're going to tell him to stamp. That's how we know where we are. Oh, right. Good point. Two people picked up on that. I'm not getting a good random integer. I'm just getting random integers. I don't need a full number though. I need a floating point number, right? So let's go ahead. Random Python. How does that work again? We need a pseudo random number. So rand range, I think. Start choice. Rand range. Let's see. Rand int, rand shuffle, rand sample. We don't need those. We want random. So, okay, random.random. There we go. Random.uniform gives me a floating point number such that the number chosen n is between A and B. Okay. So, and it is, may or may not be included, that's fine, but it's a uniform distribution, meaning that any number is equally likely. So let's go ahead and do rand. Wait, already forgot it. It's called random.uniform. Go with that one. Okay. So there we go. So let's go ahead and do a bunch of more of those. No need to. Boop, 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 boop. So now we can see that we've got a bunch of darts being thrown everywhere. So we're throwing a turtle around and doing stuff. And basically we're hitting stuff. All right, next phase though, it says before we do too much more math, we should, let's see. So now we have the animation working. Let's go ahead and add color to this to see whether or not we are hitting a location. All right, so we want to know whether or not we're landing inside the circle. We will be landing inside the circle if the distance from the center of the square, right? So if the distance from here is less than 1, because the circle has a radius of 1. So if the distance from the radius is 1 or less, it's inside the circle. Right? Does that make sense to everybody? And if it's greater than 1, it's going to be ending up outside in these spaces outside the circle. So what we'll do is that we will color anything that's inside that circle red, blue. So let's go ahead and use our Euclidean distance. We're going to import square root. So we're going to import math. So we're going to create rather than making a big if statement, I'm just going to calculate the distance. So distance is equal to math dot square root of x squared, right? I love being able to do that in Python, plus y squared. And of course, the negatives aren't going to matter because we're squaring it, and that's going to remove the whole negative value, which is convenient. So then we can say if the distance, so that gives us the distance from the center, right? The distance from 0, 0. If distance is less than or equal to 1, right? We are inside the circle. So if distance is less than or equal to 1, we are inside the circle. So that is a hit. So we are going to say Bob dot color, let's call it blue. Else we're outside of the circle. So we're going to just simply say Bob dot color is red. And so, okay, that's interesting, but it's not super elucidating. It becomes way cooler if we up this to 1,000. And also it's going a bit slow though. Ugh, right? Maybe it will time out before then, but that's annoying. Oh, right. So so let's see, simulate 1,000 dart throws and see what you get. Okay. So we simulated 1,000 dart throws and we got here. Let's copy paste this and move this down. Now that we have the animation working, we can add in the counting and make the calculation. We can speed up the animation considerably with the use of something called the tracer function. So ordinarily, the turtle draws the picture incrementally every time you do a drawing operator. So straight line. Okay. So for instance, a straight line will be, it might draw it a bit with small pauses in between every step. What we can do with the tracer is say we only perform only a certain amount of updates, and that's not important. What's important is that they have included an amount for us, I think. They have given us a, so let's see. I thought there was a line here about tracer. Oh, right. Recommend my turtle.tracer. Here we go. I knew I saw it somewhere. So we're just going to grab this and we're going to say, hey, Bob, speed up that animation, please. And you'll see that that goes considerably faster.
Can you scroll up a little bit? Where did you put
Right here. So I think I can also probably do this over here. There we go. So it goes much faster. So let's go ahead and now let's go ahead and up this to. Okay, so that's not what we needed to go fast. We need to up the other number to go faster. Saying draw, yeah, only perform. So here, let's run it now. Okay. Yep, went too long. So let's now, there we go. That went much faster. Let's go ahead and run it now. Look at that. That's beautiful. Runs much faster. Now we can go and up this baby. Now that's cool. The speed function basically just simply tells you how fast the turtle is going to draw, but I am not drawing anything. So here it's just saying basically draw a bunch of things simultaneously, waiting only a certain number of milliseconds between them. This actually is how you get it to be much, much faster. Now, look what we've created based off this. Why is the left side of the circle flattened? Because of the shape we're using to draw stuff with. We are using, currently our turtle is a very inconveniently shaped triangle. So as you notice, it's kind of jagged on the right side and flat on the left side. So let's go ahead and set our shape actually to be a bit different. We can say, Bob, hey, what's with that weird shape? Bob. Talk to me, Bob. Okay, let's go to turtle.html. Great. So, shape, parentheses. Here we go, shape. So let's see. Let's go with a circle. Bob.shape is a circle, right? That makes sense for a dot. Save and run. It's a very big circle, to be honest. I do not like it. So let's go ahead and do, let's just go ahead and throw turtle. Let's go ahead and just be literal and throw turtles at this thing. There we go. I could change the stamp to a dot, but I like this. It's fine. All right. So now that we've got our circle though, how's this going to help us calculate pi? Well, this gives us a visual representation of what's happening. We've got a circle. So what we're going to do is we're going to count the number of hits, which is fairly easy to do. Hits is equal to 0. Throws is equal to, and let's go ahead and do 10,000 throws. So for in range throws, because that's going to be our constant value. So we're going to run it now. And now we actually need to go ahead and increment because, yeah, that's something I forgot to do. And let's speed this up considerably again. So on a hit, we do hits plus equals 1. I shared there's two places. I've already shared this one. I'm not done with this, so I'm not sharing it yet. So hits, and now we can print hits, throws. So let's go ahead and run this. So we did through this and we got 7,700-ish out of 10,000. So let's go ahead and see up this. Mama's working on something to eat. So it takes about 10 times as long. Yep. So we see the ratio kind of holds over here. So what's cool about this is that basically, right, if we remember from our what we were calculating, the area of the circle is pi, the area of the square is 4. So this is the number. So this pi is going to be the number of hits. This 4 represents the number of the total number of throws, because all the throws are going to land, including the ones that land in the circle, are going to land inside the square as well. So what we can do is that if we divide by this, and let's go to 10, back down to 10,000, scroll 10,000, we get 0.7775, which isn't too exciting. Let's run it again. Okay, 0.78. So we get quite a bit of variability there, second digit. Okay, but if we take this ratio, that's pi over 4. So if we multiply this by 4, this entire thing by 4, we get 3.15, which actually is kind of expected, as they can say. If you're only going to get around 3.1 or so. To get a lot closer, you're going to repeat this simulation a lot. So what we'll do is we're going to increment this, and it's working, it's working-ish. It's going as fast as it can. So there we go, 3.12. Not very accurate right there. If we take out the drawing, actually, if we make Bob stop moving so much, we'll actually get much. You'll be unsurprised to see that we get basically a much quicker answer. Although Bob is now changing colors very quickly. Okay.
I'm gonna have Doritos. When you finish
So
those yummy foods, you said today that oranges are your favorite, right?
it's not gonna. Yeah. Okay. Take out all the drawing stuff and now do the calculations. Hopefully it will work.
I already fielded and everything for you.
Web page is slowing this down. Hey, we got 3.142344. So this is not the greatest approximation of pi, but it's a Monte Carlo approximation, which is what makes it fun. It's pretty cool. All right, so I'm gonna go ahead and skip this part, the predicting stock prices, because I don't want to have to deal with Altair, and I want to deal with the more interesting one. And if you've watched the video on the Monty Hall problem, great. If you haven't watched the video, prepare to be very confused, because this is the Monty Hall problem is also known as the Monty Hall paradox, because it basically totally messes with your way of thinking. Okay, but to review, there used to be a TV program, Let's Make a Deal, famous game show. Basically, the entire idea is that, and so the entire idea of this problem is basically, suppose you have 3 doors. So let's go ahead and Google this, the Monty Hall challenge or the Monty Hall problem. There we go, 3 doors, right? And so suppose on a game show, you're given a choice of 3 doors. Behind one door is a car, and behind the other 2 are goats. Okay, you pick a door, say number 1, and the host, who knows behind what's one of the other doors, opens another door, one of the ones you didn't choose, which has a goat. He then says, do you want to pick door number 2? Is your advantage to switch your choice? Now, I should point out that the person here is going with the assumption that you want a car as opposed to a goat, right? Whereas, you know, I'd be very happy getting a goat. You know, they're adorable. But so we're gonna go with the assumption that we want the car. Okay. So the idea here is that behind one of these doors is a car. You choose which door you want, but before he says whether you got it right or wrong, Monty goes and opens one of the other two doors you didn't pick. So if you pick door number one, he's going to pick two. He's going to reveal 2 or 3, and he's going to reveal a goat. He can always reveal a goat because there's 2 goats, right? So if you happen to pick the goat, he can always reveal the other goat. So the question is it in your advantage to switch or not? And this was in Parade magazine, Ask Marilyn's column, and Vote Savant wrote back that the contestant should switch to the other door, because under the way that the problem is phrased, contestants who switch have a 2/3 chance of winning the car, while contestants who stick with their initial choice only have a 1/3 chance. And this basically is crazy, right? Because your immediate reaction is, okay, there's 2 doors. If I switch, there's a 50-50 chance. Or if I stay put. But Marilyn's saying, no, if you switch, actually your chance of winning is higher. There is a movie with the scene. What was crazy, what this doesn't go over, is that many readers of Vote Savant's column were very vehemently kind of in disbelief. 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them claiming Vote Savant was wrong. I'm not saying that basically she got such a outrageous response because she's a woman, but I mean, like, none of the men who had previously solved this problem had gotten such a reaction. So Paul Erdos, one of the most prolific mathematicians in history, even he was unconvinced until he was shown basically a computer simulation that kind of showed it. So it is a very cool problem. So why is it 2/3? So let's suppose basically you always choose door number 1, because that doesn't matter. We can just relabel whatever door you choose as door number 1, right? So basically, here's your 2 out. So let's suppose, so basically your initial choice of door number 1 has 3 possibilities: goat, and car, right? Got 3 doors. I pick one of the doors, right? There's 3 possibilities: goat, or car. One of those 3. Got to be one of those 3. So let's go through each of those scenarios. If your strategy is right, is I pick the door and I stick with it no matter what opens up, right? What happens? Let's go through it. I pick a goat, I stay with a goat, I win a goat. Outcome 2, I pick a goat, I stay with a goat, I get a goat. Outcome number 3, I pick the car, a goat is revealed, I stay with my car, right? Because no matter what, my strategy is I'm just sticking with it. I win the car. So two goats, 1 car is our outcome. Make sense? Again, I'm very hesitant to label it as a win or a loss because, I mean, you're getting a goat. So, okay. Now, on the other hand, let's go ahead and look at the switching strategy. With the switching strategy, you pick a goat and Monty opens up the door behind the other goat that reveals the other goat. So you switch and you win. Let's go ahead and the outcome number 2, you pick a goat, right? Because there's 2 goats. So you pick a goat, Monty reveals the other goat, you switch and you win. Outcome number 3, you pick the car. Monty reveals one of the goats. It doesn't really matter which one. You stay and you win. Sorry, you stay, you would win, but you're going to switch. So you would get a goat. So this time, 2 cars versus 1 goat. Those are your outcomes, right? So another way to think about this is possibly is the way that kind of convinced me the story is that suppose you have not 3 doors, but let's say 1,000,001 doors. So actually, let's go with 1,000,000, and let's say we've got 1,000,002 doors. That's good. 1,000,002 doors. Okay. And we've got 1,000,001 goats behind all these doors. And I don't know where we're getting all these goats from, but let's say there's I mean, it's the same place that we get like frictionless surfaces in physics problems. What?
I know a guy.
You know a guy. My wife says she knows a guy. So let's say you've got 1,000,001 goats and 1 car for a total of 1,000,002. Why 1,000,002? Very well, because let's say you pick your choice, right? Now Monty is going to open up all the other doors except for 1. So he's going to reveal to you 1,000,000 goats, right? Now, is it in your advantage to switch or not to the unopened, to the other unopened door, right? Well, if you stay with your initial choice, well, you had a 1 out of 1,000,002 chance of getting the car. If you switch, though, you've got a 1,000,001 out of 2 chance of getting the car. Make sense? Because he's revealed all the goats. This is just simply on a smaller idea. But I'm sure that I know. But again, to make this really convincing, what we want to do is simulate this, right? Again, the math behind it is, let's see, does this have the math on this? Let's go ahead and refining the simple solution. So we have drawings for this. There, direct calculation. Oh, look at that. Doesn't that look lovely, right? Isn't this beautiful math? Isn't that lovely and easy to read and easy to understand? Right?
Stop. I already have nightmares from my statistics class, and that's what it looks like.
It's exactly what it looks like, right? So no, we're not going to do that. That's silly. We're going to just go ahead and just simulate this and count it. It's not really that bad. Again, the goat, yes, the goat your father bought for two zuzim. Had God ya, had God ya. Okay, so let's go ahead and but anyway, let me just say, statistics isn't necessarily hard. It's just got the same issue that I find with all of math, is that the notation is dumb. The notation is dumb, right? These are confusing notations. It is completely just, the alphabet is meant to be intimidating. I mean, why else would they use Greek letters? So, anyway, we're not going to do that. This is why I use reasonable variables for all my stuff. So, okay, what we're going to do is that we need to calculate, we're going to need to use random. Pretty much for all Monte Carlo approximations, we're going to need to use random. And let's go ahead and deal ourselves our doors. Okay, our doors are as follows. We're going to go ahead and say we've got a car. We've got ourselves a goat. And we've got ourselves a goat, right? So those are our outcomes: car, goat, and goat. Why 2 goats? Because there's two goats. You know, we've got 3 doors, and we're just simply saying what's behind them. Now, are they always going to be in that order? No, but that's what our random function is for. We've got a nice handy dandy random function called random.shuffle. Shuffle that, given a list, will give us, you know, a new configuration. So let me go ahead and see. And I think it just swaps, it alters a list. So we don't have to actually say doors is equal to new doors, right? So here, right, we can see as I'm clicking that we're getting a lot of different outcomes, right? Make sense? Right? So this is going to be useful for us because this will simulate different games. So let's go ahead and do our ID. So the way I'm going to simulate this is that, like, we're asking, is it our advantage to switch or stay? Fortunately, we only need to calculate one of those, because anytime we win when we switch would be a lose if we stayed, and anytime we won when we stayed, that would be a loss when we switched. So we can calculate. So basically, we only need to calculate one, and we can get the other pretty easily. So, what we're going to do now is that we just need to figure out how to do a game. So let's go and then we'll do a for loop to put that in. Rather than writing a for loop annoyingly like that, let's go ahead and create a game. So def game. It's gonna no need to take any arguments in. What we're gonna do is that we're just gonna simply say, here's our door. Let's go, here's the doors that have been created. Let's go ahead and shuffle the doors. Now, like I mentioned before, I'm always going to pick the first door. It doesn't matter which door we pick. I'm just always going to pick the first door because that is the easiest. That is the easiest way to do this. So our choice is equal to. And actually, why don't we go ahead and basically put in a strategy. So if this is true, we're going to stay. If it's false, sorry. If switch is true, we're gonna switch. If switch is false, we're gonna stay. So our first initial choice of a door is going to be always door 0. Make sense? We're always going to pick that as our initial choice. So now Monty is going to reveal our other door. So let's go through the different scenarios. If doors 0, let's just think about this. So if door 0 is equal to a goat, right? Then what's going to happen? Monty would basically say, hey, here's your other goat. Do you want to switch? Yeah, there's no need to do this because we've already kind of walked through it. So if door 1 is equal to goat, then we're going to switch. So if the door is equal to goat, he's going to open the other one. We're going to switch to the car. So that will just simply be a win for us. So return true to represent that we won. Else return false to represent that we lost. Make sense to everybody? So basically, we're going to win every time we choose a goat because we're going to switch because he's going to reveal the other goat and then we're going to switch. And another one's going to be the car. So, okay. For I in range, let's do 10,000 of these games. 10,000 Monte Carlo simulations of the Monty Hall problem. A full Monty, if you will. Yes, I do need 2 equal signs because I've totally forgot. Okay. For I in range 10,000. Let's go with wins is actually, let's go ahead and do wins, games. Wins is equal to 0, games is equal to 10,000. Right, so let's do games. Okay, if game, so if game equals true, so in other words, if we got a win, wins plus equals 1. Otherwise, we don't have to bother counting anything because we're only counting the times we win. Print wins out of games. And we win 2/3 of the time. All right, that's close enough to 2/3. So questions about this? Did I abstract it away a bit too much or I don't want people to be confused about it because it is a confusing kind of it is a paradox.
I keep getting numbers in the 6 point something range.
Are you multiplying?
Yeah.
0.6, it should be 0.6, right? So numbers divided by games, and then I put games over here. Make sure you're dividing also by the right number. That's why I changed this to games, so that I could just change one thing, and then I could do I could change that in one place.
Oh, range games. Oh, whoops.
Yep. That way I can change the number of games I run and not worry about any kind of issues I'm having.
Okay, I get it now. I had 10,000 in the range with
Mhm.
games instead of games being in the
Right,
range.
right. I switched that. I was doing that.
Okay.
Yeah, sorry, my bad. So
No worries. This class moves too fast for me to notice small things like that.
that's why I record. So, all right. So, so there is that. I'm gonna leave aside the Altair stuff because that is kind of just kind of annoying. All right, so share the code. Sure, it's not particularly because mainly I'm not as comfortable with it as I should be, or as the book wants me to be at the moment, and it's just more interesting to take a look at these kind of Monte Carlo simulations and kind of do that. And I mean, we can do this with any kind of, so this is, sorry, the things we've been looking at are Monte Carlo simulations for things with a single outcome. But what about if we want to keep track of multiple outcomes, say on rolling 2 6-sided dice? Very classic kind of thing you do on a lot of different games. For instance, Monopoly relies off of rolling 2d6. So for the 2 6-sided dice. So let's go ahead and I'll open up my code. So I'll open up idle for once. Idle doesn't get enough love. So let's go ahead, new file. Let's go ahead and.
Want us to follow along?
You can, but I mean, I can always share the code with you guys. So let's go ahead and do dice outcomes, I'll call this. So like I said, what we're going to need to do is we're going to need to import random. Pretty much any time we are working with Monte Carlo, you need to work with random numbers. Now let's go ahead and talk about, so I'm going to go ahead and basically create a function called roll do d6 to d6, not f6. So first off, a bit of dice notation. I am a Dungeons and Dragons and other RPG player. So I do like to use RPG dice notation, which is quite simple actually, which is that basically if you say 1d x, that means you're rolling 1 x-sided die. So if I'm rolling 1d10, I've got a 10-sided die. Classic thing for Dungeons and Dragons is that it relies off of 1d20, a 20-sided die, right? So you roll that and it gives you a random number between 1 and 20. Okay. On the other, so if I'm putting in a notation like 2d6, which as any Dungeons and Dragons player knows is the amount of damage that a greatsword will deal, then that is rolling 2 6-sided die. There are some so typically what we the worst die, of course, is a 1d4, mainly because it's a triangular prism and therefore it makes a great caltrop. So that's why it's the worst, because it's easy, because these things are easy to drop and they're like worse than Legos to step on. Okay, so anyway, that's neither here nor there. So let's go ahead and simulate rolling 2 6-sided die, by which I mean what we're going to do is that what you care about is not the physical part of the die, but when you roll something, what is the outcome, which is in this case 7, right? So to do that, we're going to need to generate 2 random numbers. Okay, now the reason you have to generate 2, now why do I have to generate 2 random numbers? Why can't I just simply generate a number from 2 to 12? Anyone?
Because it's more likely you'll roll a 7 rather than a 12 or a 2.
Right. Each of these die has to be simulated independently of one of another because of the way, because each of them operate independently of each other. Yep, they're mutually exclusive events. So you can't just simply say, give me a number between 2 and 12. You need to simulate each of these individual dice because they're each an individual event. So, and if you roll them enough time, and we see that if we roll them enough time, if we roll one, it's going to give you a random number between 1 and 6. If you roll another one, it's going to give you a random number between 1 and 6. What is the average of those two? So what is the average of rolling a 6-sided die? Right? It's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. The 6 different outcomes you can have divide by 6, which is going to be somewhere between 3 and 4. Right? So that's why you get, so you've got 2 of these things, it's more likely you're going to get 7. Long story short, if you're rolling dice, plural, simulate them together. Right? And this is why, like, so this is why I'm going to do it like this. So die 1 is equal to random dot, and here I can use randint correctly. 1 to 6. Die 2 is equal to random dot rand int 1 to 6, right? And we're going to go ahead and do die 1 plus die 2. And we're going to go ahead and return that. I'm not really sure. Let me see what rand range does to figure out what that is. Import random dot rand range 1 to 6. Not really. I think rand range, let's see. Not getting a 6, which means that rand range is mutually, I think rand range is the whole going up to, but not including an amount, I think. But, I can't say for certain because based off of what we've seen, it could have been that I'm unlucky, but let's go to rand range. Start, stop matches the pattern of range. So keyword argument should not be used because, okay. So yeah, so it goes up to, but doesn't include stop. So it's the entire, so it matches the way range works. Okay, rand int gives you the way that you kind of want stuff to happen, which is a random number between these 2 numbers, please. So let's go ahead and print roll 2d6. Now, we can run this. Yep, run it. And we run 11, 9. So we're getting random numbers. Okay, let's go ahead and calculate what the expected value is in statistics term. In other words, what are we going to get if we run this a bunch of times? So let's get what the average is of like rolling this a ton of times. For total is equal to 0. Rolls is equal to, let's do 10,000 rolls. For I in range rolls. We are going to just simply say total plus equals roll 2d6. So basically I'm going to roll these die. I'm going to roll 2d6 10,000 times, sum it all up. And then what we're going to do is we're going to take the total and divide it by the rolls to get the average, which should be somewhere like 7-ish, I think. Total divide by rolls. So we run this, it does the calculations, it yells at me because I forgot a colon, because I make those kind of mistakes too. And I get something pretty close to 7. Yeah, and mind you, the more of these that I do, the more exact I can be with my answer, right? The number of decimal points start kind of increasing. And the more sure I can be of my answer. Right, so this does take, so doing 10 million rolls seems to take a bit of time, but we got something that's pretty darn close to 6. Oh, sorry, to 7. Okay, but we're just keeping track of one single outcome. What if I want to keep track? If I want to keep track of this distribution of all the outcomes? What if instead of calculating how many rolls, I want to see kind of like how are things distributed? How many 2s get rolled? How many 12s get rolled? How many 6s? How many 7s? How many 5s? Right? So for that, what we're going to do is that we're going to use a dictionary. We could use a list and assign each index, but a dictionary is better in this case because it's more general use. So instead what I'm going to do is I'm going to create a dictionary called outcomes. Is a dictionary. So what we're going to do is we are going to roll 2d6. I'm going to store it, whatever I get from 2d6 in result. Make sense so far? I'm going to roll 2d6. Okay, I got a 9. That is my result. So what I'm going to do is I'm going to take a look at my outcomes dictionary. I'm going to say, hey, have I seen that outcome before? If result not in outcomes. So if I haven't seen it before, I prefer this notation first. Well, that's the first time I've rolled this outcome. So I'm going to say outcomes. Let's keep track of that outcome. So outcomes of that result is equal to 1. That is the first time I've seen that. So I've seen this result once and it's stored in outcomes. Otherwise, if I have seen that result before, right, I've either seen it or haven't seen it. It's only 2 possibilities. So if I haven't seen it before, what am I going to do? Outcomes, results. Well, I've seen it one more time. Ta-da. And now what I can do is that now that I'm done, I can print outcomes. Print all the things that name results isn't defined. Right, boom. So, and this printed out in the orders that things were rolled. So the very first result was rolled was a 9. It says, so we've got all these different results here. Got a lot of 8s, a lot of 6s, and a lot of 7s. So let's go ahead and see this. Do I need outcomes.keys? No, it automatically translates it to outcomes.keys. So what I'm going to do over here is that maybe we should print it sorted. So let's go ahead. Something I always have to look up. How to print dictionary sorted by keys. Readably print out right. Probably would just want to do pprint, stuff like that. Oh, we could always just do, oh yeah, right, duh, simple. So for result in sorted outcomes dot keys. So here, for result in sorted outcome.keys. So basically I'm saying, hey, sort these results. Print result and then outcomes result. So print out the thing we rolled and the number of times we rolled it. And now we get a nice table of how many things we got, of what all the results were when rolled. We can do one better, and we can even say, we can make this a bit more statistically useful by saying outcomes result, the outcomes of that result divided by the number of rolls we did, and that will give us the percentage. Or it would give us something out of this, which we could just simply, let's go ahead and prettify it, make that pretty, times 100, and then we're going to go, I'll put parentheses, even though orders of operations would ensure that it's doing that what I want it to do, just to be clear. And then what I'm going to do is I'm just going to go ahead and add the percentage sign to it. Oh, and I have to convert that all to a string. Now we can make this pretty, and there we go. Well, kind of pretty, I guess. We've got, those trailing things that we could format if we needed to. And then let's go ahead and do sep equals tab to make it line up a bit nicer. Just a bit nicer. So there we've got our results. We've got what we rolled, right? Which is all the things you can get on 2d6. All the things that we got, all the outcomes, and all the, and all the percentages. So if I wanted to calculate this for something a bit else, or something else, I like say, let's say 3d6. This entire thing works, and all I have to do is just change the function. Let's go ahead and generalize this out. Roll x d6, where x is the number of dice, and total is equal to 0. Return total. Okay, for I in range. Yes, I'll send the print line over here. Yes, Pavel, what is it?
Why on line 13, why is total equals 0? I'm not too sure.
Line 13? I just started it. What I'm doing is I'm creating a total, and now I'm going to go ahead and add more to it.
Okay.
I'm going to add numbers to it. You always got to start at 0 because you need something to store, because I'm defining a variable called total that I want to store numbers in. I'm running sum. So total in range x. I want to do this x times, which is total is equal to what we previously had in total plus a random number between 1 and 6. So this represents us rolling a die. And this will happen x times. So if I put in 2, this is going to be 2d6. If I put in 4, it's going to be 4d6. Make sense? Okay. So now what I can do is say x d6. It's going to be, if we put in 2, it should basically print out very similar results. Those look a bit similar. We did 10,000 rolls, and you can see with 10,000, you get a bit of variability. Let's go ahead and roll 8d6, which of course, as every Dungeons and Dragons players knows in 5th edition, is the amount of damage you would get off a fireball. And we see that basically that the damage peaks there around 28 points of damage. 27, 28, 29, somewhere around that. In order to know precisely which is the most likely outcome, we need to do a lot. I'm doing 100 times the number of runs here, and now we get a bit more of an exact result because the number of simulations I did ran up. It always helps to do more simulations. Less simulations isn't that good, right? Over here, this doesn't necessarily give me a good accurate representation because I'm rolling 8 6-sided die. There's more than 10 possible outcomes. So this really does not present with a very good result. So you need to have plenty of trials to get like at least 1,000, even to get like a reasonable number. And even then it can still lead to like some erroneous results. The more simulations you do, the more accurate your result is going to be. So the Monte Carlo, again, the entire idea of a Monte Carlo simulation isn't that we are not exactly solving it like you would in probability and statistics or in calculus or in differential equations. The entire point, we're not solving. Solving is hard. What we're doing is that we're counting and we're getting a very good estimate. A very good estimate that will tell me with some likelihood what the outcomes are going to be. And some events are really rare, as we can see. We rolled this 1,000,000 times, and only once did of all the eight D6s did we get everything come up all ones, which can happen. It can happen, but it's super rare. Similarly, it doesn't look like we ever hit a 48 once. So this was not enough simulations for that. Right? So we didn't get all the possible results. So let me go ahead and drop this in chat for you. And even on my super duper computer, I like to call it a super duper computer, even though, but that's just like me bragging. So, but even on my pretty high powered computer, it takes a while to do these, to do a good number of simulations. Although that could just be running in idle. It might run quicker if I were to run in something else. Still running performance. Yeah, idle's just not optimal at doing all the number crunching that it needs to. Plus, Python's not great at exploiting anything multi-threaded. All right. So with that, I think that I will leave you with that. So let's stop recording. All right, so I will be available after class if people want to talk. So just give me 1 minute, but class is dismissed. I will upload the videos. I think I didn't upload last week's videos. I will have to do that along with this one. Oh, and everything just printed out. So, okay.